Document camera. What's your problem? There we go. So I was planning on talking about parts of derivatives, but I imagine people might have some questions about other things that we could entertain for a moment if you all want. So I guess I'll open up the floor to, are there any questions about any things that you would like me to talk about? Sure. We can definitely continue talking about that. Um, I was going to show a couple delta epsilon type proofs of ones that exist. If has anyone done that in class? Cool, then we won't do it. That said, if we think we need to talk about it, then I'm happy to at some later point. So let me grab my examples here. Where'd you go? So let's look at some more examples of multivariable limits, which are the things we were doing last time. Multivariable, variable, I can spell, maybe, sure. Close enough. So let's look at something like this. The limit as x comma y approaches 2 comma 3 of 3x squared plus xy minus 2y squared all over 3x minus 2y. And as you can probably all guess, if we plug in 2 for x and 3 for y, what do you think we're going to get? And on the top. It's pretty typical. We should check. You plug in 2 for x and 3 for y, we're getting 3 times 4 plus 6, which is 12, minus 2 times 9, which is, sorry, 12 plus 6 is 18, minus 18 is 0. So we're definitely getting a 0 over 0 type. And normally, so the way these problems often work out is if they want you to test paths, it's almost, not always, but almost always going to be through 0, 0. If it's through another point, testing paths is a more challenging but not impossible process. In fact, I think I have one over here that's not bad. But here, instead of testing paths first, I'm going to try to see if I can factor something. So you should at least look to see, can I make a factoring work? And this one you definitely can. So here's what I would point out. The factor that's problematic is the 3x minus 2y. I would love to be able to factor exactly that out of the top. So I'm just going to guess that that's going to work. So on the bottom, I have 3x minus 2y. On top, I'm going to pretend like, well, I know it's going to be a 3x minus 2y, and then I'm going to fill in the other pieces that are going to make this work. Let's see, I would have to have an x, so that 3x times x is 3x squared, and I'd have to have a minus y, so that negative 2y times negative y, oh, sorry, a plus y, so that negative 2y times y is negative 2y squared. And then I'm going to check to make sure that the middle terms add up to what I actually have. And they do. I get a negative 2x times y, and I get a positive 3x times y, and those together add up to my x times y. So this factoring completely works. The 3x minus 2y's cancel. We're left with the limit as x, y approaches 2 comma 3 of just x plus y, which is just 2 plus 3, which is 5. Let's contrast that with this next example. The limit is x comma y approaches, can I make this type bigger? Yes, I can. Approaches 1, negative 1 of the x plus y over x, y plus 1. And again, you will probably observe that if you plug in the point you're approaching, you're going to get 0 divided by 0. And in this case, unlike the last one, I don't see an obvious way of factoring anything. Like, not at all. So if I don't see any potential factoring or some other sort of thing I might work on, oh, that's an interesting idea I just had. I would probably start looking at different paths. Now, usually our limits approaching 0, 0, and so our paths are nice things like y equals x, or y equals x squared, or y equals x cubed, or some power of some one of your variables. In this case, that's less of an option, although not completely not an option. You could certainly pick x equal to y squared as one of your paths here, because this goes to the point 1, -1, which is on the graph x equal to y squared. But I would make easier choices first. Like a really easy choice is the path x equal to 1. This limit that's approaching the point 1, -1, definitely the line x equal to 1 goes through that point. So if we try that path, we're going to have the limit as y approaches -1. We're not going to write the x is approaching 1 because x is equal to 1. And then we're just going to replace every x with 1 and that's it. And now the limit as y approaches -1 of 1 plus y over y plus 1, well, 1 plus y divided by y plus 1 is always equal to +1. So we have the limit as y approaches -1 of 1, which is just 1. So now what we hope to do is find a different path that gives us a different result, because then we can say the limit doesn't exist. And I think there's another obvious choice. I want you to make it and try it. What's the other similarly obvious choice as the path x equal to 1? What's that? Oh, so I don't think L'Hopital's rule is viable at all in this context. So I'm not saying use a different method. I'm saying pick another path. Instead of x equal to 1, what's an equally easy path to observe that would contain this point? Y equals -1. That is equally easy in my opinion. So try letting y equal -1 and see what your limit ends up being. So let's see, if we pick the path y equal to -1, we're gonna have the limit as x approaches +1. We're gonna have x plus -1 on top and x times -1 plus 1 on the bottom. And on the bottom, if you factor out a -1, you're left with x minus 1. And so this simplifies to the limit as x approaches 1 of 1 divided by -1, or just -1, which is going to be -1. Two different paths, two different results. Limit doesn't exist. So we can conclude the limit as x, y approaches 1, -1 of x plus y over x, y plus 1 does not exist. Nope, sorry. For the most part, this is what you're hoping for, right? You're really hoping your limit doesn't exist, because if it exists, it's usually kind of a giant pain, unless you happen to be fortunate to have something like this first one that factors, or something like this next one. Say the limit as x, y approaches 3, 2 of the square root of 10 minus x times y minus 4 over xy plus 6. Now, again, looking at this limit, if you plug in 3 comma 2, you're going to get 0 over 0. You're going to get the square root. Except I think I made a mistake. So let's actually observe that. Let's actually, no, I don't love that mistake at all. Yeah. Oh, I did. I see my mistake. It's okay. So let's actually, let's say this got written on your test. Your instructor made a mistake. They gave you this limit. Go with it. So I am almost about to make the error of not doing what I say we should do every time, which is you should plug it in and check. Because if we plug it in, we get the square root of 10 minus 6 minus 4 over 3 times 2 plus 6, which is looking like the square root of 4 minus 4 over 6 plus 6, which is negative 2 over 12, which is negative 1/6. Cool. That's my answer. I'm done. What my teacher meant to write, but made a mistake writing, and if they don't catch it, we're in luck, is what I meant to write was the limit as x comma y approaches 3 comma negative 2 of the square root of 10 minus xy plus 4 over xy plus 6. But if you have something nice like this that happens to just come out to be a not 0 over 0, then don't say anything. Like, and maybe it might be on purpose, right? Your teacher, I mean, yes, sometimes people make mistakes when they write exams, but this could totally be a question they wrote thinking that people were going to assume it's a 0 over 0, and it's not. So you should always be checking. All right, but here, if we plug in 3 negative 2, if we actually check, you're going to get the square root of 10 minus negative 6. Again, mistakes. So that should be a minus 4, and I don't want to address if it's not. So that's a minus 4 there. Sorry about that. Minus 4 over 3 times negative 2, which does end up giving you a 0 over 0. Question?
What if you did it was a plus 4?
Then it's super duper annoying because you have a non-zero over 0, which means you limit some sort of infinity. But since you've got multiple directions, it's probably infinity from some directions and negative infinity from other directions, so it's going to not exist. Yeah, it would definitely would not exist because there's yeah because you'd have.
That wouldn't be something.
But no, it's not something it's not something we want to really talk about just because it's not interesting. Is really the truth. So here. Unlike the previous one where like you could try some different paths here, right? You could try the path x equals 3 and y equal to negative 2, but it's kind of super annoying. In fact, if you try the path x equal to 3, you're going to have the limit as y approaches negative 2 of the square root of 10 minus 3y minus 4 over 3y plus 6. And what you would do here, I'm not going to do it because I don't want to, but also because I don't want to do all the work, is we would try to evaluate this 0 over 0 type of limit because it's still 0 over 0 if you plug in negative 2. Say it, what? You could use L'Hopital's rule here. I wouldn't, but you could. I would prefer just to multiply by the conjugate. But that begs the question, why didn't I do that in the original function? And I can. So what I should think about trying here is say, okay, well, I'm going to take my original thing, square root of 10 minus xy minus 4 over xy plus 6, and multiply by the square root of 10 minus xy plus 4 divided by the same thing. Now we get in the numerator, and I am going to do some simplifying on the fly here. In the numerator, we're going to get 10 minus xy minus 16. And 10 minus xy minus 16 is equal to negative xy minus 6, or negative 1 times xy plus 6. So my numerator here, when I multiply these out, is going to be negative 1 times xy plus 6. My denominator is xy plus 6 times the square root of 10 minus xy plus 4. And then the xy plus 6's get to divide to 1. And we're left with negative 1 divided by plug in 3 for x and negative 2 for y. The square root of 10 minus negative 6 plus 4, which is going to be negative 1 over 8. Now, I will point out, if we had done what we like, if we'd actually done this limit here, we also would have gotten -1/8. -1/8. But really, the fact that we saw this, we're like, oh, we can multiply by a conjugate kind of informed us that, well, we could try that in the beginning. So what I'm trying to say is some of your algebraic methods from 21A still work just fine. But I should emphasize here, L'Hopital's rule is not an option for multivariable limits. Sure, single variable, you could totally use L'Hopital's rule here, but that's still not going to help you know if the overall limit exists or not. Because again, you can find as many different pathways as you want where the limit exists is equal to the same thing, but you can do that 100 times and still not prove that the limit exists. To prove the limit exists, you have to either be able to factor and cancel or do some other argument we talked about last week. Is there a question? Sure, from here to here. Yeah, so when you multiply this out, which I admit I did not show, right? When you multiply something by its conjugate, you end up getting I don't really have the room here, let me see. So just to say what I did is the square root of 10 minus xy minus 4 times the square root of 10 minus xy plus 4 is equal to this times this, which is 10 minus xy. And then you have this times 4 and -4 times that. Those cancel out. That's the whole reason you multiply by the conjugate, so that the middle terms add up to 0. And then you have -4 times 4, which is -16. And then simplifying, you get 10 minus 16, which is -6 minus xy. And then I knew I was trying to cancel out an xy plus 6, so I factored out the -1 and said it was -1 times 6 plus xy, or xy plus 6. Right. So specifically, when we have a square root and you want to get rid of that radical, multiplying whatever you have where the root is by its conjugate always accomplishes that. Because when you multiply some a minus b by its conjugate, you get a squared plus ab minus b squared. The middle terms cancel, and the first term gets squared, getting rid of the radical, and the second term gets squared as well, getting rid of a radical. There's one there as well. So that's why we multiply by a conjugate. There's a square root of the problem. Okay. One more. And I do feel like we should talk about partial derivatives. Where'd you go, example? Yeah, sure. So let's look at this one. It's number 4, 5. The limit as x, y approaches 0, 0 of x cubed times y over x to the 6 plus y squared. Okay, someone volunteer and tell me what is one of the paths I should for sure. Oh, okay, first of all, 0 over 0. Right? Plug in 0, you get 0 over 0. What is for sure one of the paths I should try?
Either X or Y.
Thank you. Yes, either x or y equals 0. Always, every time, try at least one of those. So sure, let's try x equals 0. Usually it's going to yield 0, but not always. So the limit as y approaches 0 of 0 times y over 0 plus y squared. And notably, this simplifies to 0 divided by not 0, which is the limit of 0, which is 0. So what's that?
It's still 0 over.
No, it is not. And that is what I want to emphasize strongly here. It is not 0 over 0. Because before we are saying that y is 0, we are saying that this expression is 0 divided by whatever y is. Y is not 0, right? It's approaching 0. It's not 0. So y is getting really, really close to 0. But before y gets to 0, we're saying, well, 0 divided by this really small number squared is 0. And then the limit of that is 0. So that is the power of using this path, is it gets you the 0 before you're plugging in the 0 for the y. Right. Again, we're asking the question when you take this, you're saying as y gets really, really close to 0, what does 0 over y squared end up getting close to? Well, if you've got 0 divided by something not 0 squared, it's 0 the whole way through. Right? 0, 0, 0, 0, 0, 0, 0. Then maybe something terrible happens at the origin, But as far as up until it's happening, it's zero all the way. Okay, but now we need another path. Now I'll point. What's that? Well, as I say, picking y equal to zero is probably going to give you the same result, right? Because if you pick y equal to zero, you're going to get zero on top and x to the six plus zero on the bottom, which will simplify to zero because it will still be zero, right? Your goal at this juncture is to pick another path that doesn't have the same result. Y equals one doesn't go through the origin. I would pick y equal to x to some power or x equal to y to some power. So sure, that's a great choice. Y equals x, let's see what happens. You get the limit as x goes to zero of x cubed times x, which is x to the fourth, over x to the sixth plus x squared. And if you plug it in right away, you're still going to get zero over zero. Here, you have to do some factoring. You typically have to look for and identify the smallest power of x. So I see that I have an x squared there. So I'm going to factor out an x squared from the bottom. I have the limit as x goes to zero of x to the fourth over x squared times x to the fourth plus 1. The x to the fourth over x squared cancels that x squared and gives me an x squared on top over x to the fourth plus 1 on the bottom. And bad news, I get 0 over 1, which is 0. I need a different path. Sure, let's try it. So y equals x squared. I'm going to have the limit as x goes to 0 of x cubed times x squared over x to the sixth plus x squared squared. So that's going to be the limit as x approaches 0 of x to the fifth over x to the sixth plus x to the fourth. And at this point, you might notice that the same kind of thing that just happened is going to happen again. Hold on. If I factor out an x to the fourth from the bottom, I have x to the fifth over x to the fourth times x squared plus 1. Cancel that and all those. And then you have the limit as x goes to 0 of x over x squared plus 1, which is 0 over 0 plus 1, which is 0. Go ahead. I'm sorry.
Do something crazy? Like, would that help doing like a really weird function?
I would say no. So here's what I'll remind you I said last time. You're trying to look for a choice that's essentially going to give you all of your powers the same in the numerator and the denominator. So what could you pick y equal to that would for sure give you the same power of x in both the numerator and the denominator for all the terms? Not a square root. I could pick y equal to, well, look there. I've got y squared. I would love for y squared to be x to the sixth. And I'm not adding powers, I'm multiplying powers. 3. We want to pick y equal to x cubed because then in the denominator, the x cubed squared will be x to the sixth. And then the numerator, x cubed times x cubed will also be x to the sixth. These are usually set up in a way that there is going to be a choice that makes things work out nicely. Watch what happens. So if we pick y equal to x cubed here, we get the limit as x approaches 0 of x cubed times x cubed over x to the sixth plus x cubed squared. That ends up being the limit as x approaches 0 of not 2, of x to the sixth over x to the sixth plus x to the sixth is 2x to the sixth. And then we can divide, say that's the limit as x goes to 0 of 1/2, which is 1/2, which is not 0. So now that we have multiple paths being 0 and one of them being not 0, the overall limit does not exist. But it is kind of a pain to have to think of what the right path is that makes it so that works out. Question, yeah. Right. Most of these limits where it's a 0 over 0 type, unless there's some sort of nice factoring like we saw in a couple problems, if you're getting 0 over 0, it is usually we usually approach these problems with the thought that the limit's probably going to not exist. And so our job usually is to find two different paths that give you two different results. So yes, I would say that's how you should approach these problems if it's a 0 over 0 type that you cannot obviously factor or use some sort of algebraic method for. because showing a zero over zero limit does exist when it exists is kind of terrible. We talked about a couple examples at the end of class last time where we used either a squeeze theorem argument or we used polar coordinates to show that the limit existed. You were here, weren't you?
Yeah,
Okay.
I forgot about
All
that.
right. Yeah. Sorry. Here's the appendix form. So, yeah. Do I want to say more about that? Not really. Yeah. Okay, let's talk about partial derivatives because we should talk about partial derivatives. So good news, partial derivatives are super easy. If you know how to take derivatives. If you know how constants work when you take derivatives as well. So as a reminder, what's the derivative of 6 plus sine of x? Right, because the derivative of 6 is 0, and the derivative of sine of x is cosine of x. And as another reminder, what's the derivative of 6 times tangent of x? Right. So what I'm broadly trying to point out here is that when you have a constant added to your stuff, its derivative is 0. Or constants by themselves, their derivative is 0. But when you have a constant multiple of your function, it sticks around, right? The derivative of a constant times your function is the constant times the derivative. Those are the important pieces we have to remember moving forward. So now, yeah. Yeah, I don't really want to talk about that just yet. We'll come back to kind of the idea. So let's look at some examples, and then we'll come back around and talk about kind of the idea of what's happening here. But let's say we have this function, f of xy equal to x to the fourth plus 2y cubed plus x squared times y to the fifth. And we're going to find the partial derivatives with respect to x and y and some of the second partials as well. So there's a couple of different notations for partial derivatives, just like there's a couple of different notations for regular derivatives. You either have the Leibniz notation, the dy dx, or the prime notation, f prime of x. Well, here we have two different notations for the partial derivative with respect to x. You can either say it is del f del x. A del is just a curly d. Or you can say it's fx. F with x as a subscript. You don't say f of x. You don't say anything between the f and the x. It is fx. That is the correct way to say that. And what we're going to do is we're going to essentially say that x is our variable and everything else, every other variable, y, is being held constant. So the derivative here, well, the derivative of x to the fourth is 4x cubed. The derivative of 2 times this constant cubed is 0. And the derivative of x squared times the constant is 2x times that constant. So you just pretend like the variable that you aren't, or I should say, you pretend like the variables that you aren't differentiating with respect to are constants. And so if they're multiplied by something, they hang out. If they're just their own thing without any variables, their derivative is going to be 0. Yes.
The concept class is still or its original form.
Yes.
And then let's say in the case where like if it's finding the partial derivative for y,
Which we're about to do.
that constant comes down to the bottom, right, of the y.
Right. So like when we take the partial derivative of f with respect to y, which we could call fy, the derivative of x to the fourth is going to be 0. The derivative of 2y cubed is going to be 6y squared. And the derivative of the constant x squared times the function y to the fifth is going to be x squared hanging out, just like 6 hung out up here, multiplied by the derivative of y to the fifth, which is 5y to the fourth. And I would certainly probably write this actually as 6y squared plus 5x squared y to the fourth. Okay. There's also second partials. In fact, you can take as many partial derivatives as you want. So Yeah, let's go down here. Sure. So the second partial derivative of f with respect to x, you could either write as del squared f del x squared, or much more compactly as fxx. And all we're going to do is we're going to look at our first derivative with respect to x. So it's going to be the derivative with respect to x. I should say the partial derivative with respect to x of the first partial derivative with respect to x, which was 4x cubed plus 2xy to the fifth. So now we're going to differentiate that with respect to x. And it's going to be 12x squared plus the derivative of 2x is just 2 times the constant that's just hanging out there. If we took the next partial derivative with respect to x, we would get 24x plus 0. Similarly, the second partial derivative with respect to y, del squared f del y squared, or fyy, is the derivative with respect to y of our partial with respect to y, which was 6y squared plus 5x squared y to the fourth. So differentiating that, we're going to get the derivative of 6y squared is 12y to the first. The derivative of this constant 5x squared times y to the fourth, the constant multiple hangs out, and the derivative of y to the fourth is 4y cubed. Sorry. And then you should simplify that, right? I would write that as 20x squared y cubed. All right, so if someone asks for all the first and second partials, we found all the first partials, but there is another second partial. There's actually two more, the mixed partial derivatives. And I've got some bad news notationally. So we have del squared f del y del x means you do the derivative with respect to y of the derivative of f with respect to x. So that's going to be del del y of my first fx, which was 4x cubed plus 2xy to the fifth. So now we're differentiating this with respect to y instead of with respect to x, which is kind of easier in this case. The derivative of 4x cubed is going to be 0. The derivative of 2x times y to the fifth, well, 2x is a constant multiple as far as y is concerned, and the derivative of y to the fifth is 5y to the fourth. So we end up getting 10xy to the fourth. And here's the bad news. The bad news is if you write this in the other notation like this, well, we differentiated with respect to x first and y second, so we're going to write this as fxy. And notably, they're out of order from each other. And that is how it is written. And that's just something we have to deal with. Yeah.
So the 4x cubed becomes
Right.
0.
We're differentiating 4x cubed with respect to y. And since there aren't any y's in there, it's a constant and its derivative is 0.
Y,
Uh-huh.
and then partial right, partial y, partial x.
Right.
So this either way, no matter how you write, you still get the same output. Like,
Well, so hold on to that thought. So one thing I'll point out is when you're reading it in this notation, you read it from right to left. You're doing the derivative with respect to x first and then y second. Whereas this notation, you read from left to right, x first, y second. And then let's actually look at the mixed partial derivative the other way. So if we calculate del squared f del x del y, which would be fyx, it's going to be the derivative with respect to x after we've already done the derivative of f with respect to y. So it's going to be the derivative with respect to x of our del f del y, which was, looking back at my notes here, which was 6y squared plus 5x squared y to the fourth. So that is our first partial derivative with respect to y. And now we're going to take the derivative of that with respect to x. So the derivative of 6y squared is 0. The derivative of 5x squared times this constant y to the fourth is exactly. And you might notice that these are the same. And unfortunately, that is not always true. Fortunately, it's mostly always true. you have to come up, so any function that looks, any multivariable function that looks normal is generally going to be true that the mixed partial derivatives are the same either way. Doesn't look weird. Let me just hold on, I promise you. Give me 1 second. So let me show you if I can find it, because I never remember what it is. Where'd you go? Sorry. I think it's right here. Nope. Where are you? Sorry. So, fine. There's a theorem called Clairaut's theorem that talks about when the mixed partials are equal to each other. And there's this whole condition about how basically if the mixed second partial derivatives are continuous, then they are equal to each other. But what I really want to show you is the example, which I know is in my notes somewhere. I just don't know where exactly. Yeah, here it is. So here's kind of the classic example. So here is one of the simplest functions where this fails. So this, wow, I can spell, right? This function, f of xy equal to xy times x squared minus y squared over x squared plus y squared, when as long as the coordinates aren't both 0, and then 0 if they are both 0. This function is one of the simplest examples of a function that fails to meet this criteria. So this function, yeah, it's a real function, fails to have the mixed partials equal to each other. And at least at this juncture, I'd say you shouldn't stress too much about this. Now, if one of your teachers goes off on a big old tangent about how this is important, then we can talk more about it. But at this point, I would just say, so, right, one of the easiest examples of a function where this doesn't work is a piecewise function, right? Most of the functions of two variables that we are looking at are not piecewise functions. They're just a nice, like, stuff with x, stuff with y, added, subtracted, multiplied, whatever, but not some thing where you have like different pieces equal to different things. So I would say at this point, don't worry about it. You still need to be able to correctly take the partial derivatives in the right order, but it should be kind of what's reassuring that if you accidentally did the mixed partial derivative in the opposite order, you should still get the same result. So what are we really doing here with these mixed partial derivatives? Well, let's look at kind of this example. Let's look at my favorite paraboloid, f of xy equal to 9 minus x squared minus y squared, which I'm going to try to draw. I can draw that, that's fine. Sure. Let's just draw it nicely. So it's got an x-intercept of 3, 0, 0, a y-intercept of 0, 0, 0, 3, 0, and a z-intercept of 0, 0, 9. And what we're going to do is we're going to look at what's happening at, sorry, let me grab my, sure. Yeah. Let's look at what's happening at the point 1, 2, 4. So we're going to go 1 in the x direction, 2 in the y direction, 4 in the z direction. So we're looking at like something. So we're on the level curve where z is equal to 4. And we set the function equal to 4. 9 minus x squared minus y squared equal to 4 essentially becomes 9 minus 4 equal to x squared plus y squared. So the view from above is we're on a circle of radius square root of 5. And we have gone 1 in the x direction and 2 in the y direction. So we're looking like right there. So we're looking like right there. And if we're asking what the partial derivative with respect to x at this point is, the question we're really asking is, what is the slope of the surface if you move just in the x direction? Specifically, when I say the x direction, I mean towards you in the positive x direction. So, well, let's take a look. If we hold y constant, then, right, if y is equal to, was it, where'd you go? I didn't write my point down. 1, 2, 4, I think. Yeah, 1, 2, 4. So if y is equal to 2, then my function is going to be f of x comma 2 equal to 9 minus x squared minus y squared, which is just going to be 5 minus x squared, which looks like this. And on that parabola, if we move along that parabola, the height's changing and x is changing, but y isn't changing. Y is equal to 2 everywhere on that green parabola there. So now we're asking really, at this point, if I move forward towards you, what's the rate of change or what's the slope of my tangent line there? Well, easy enough to calculate. My partial with respect to x is equal to 0 minus 2x minus 0. And if I plug in my point, 1 comma 2 comma 4, it's just going to equal negative 2 times 2, which, sorry, negative 2 times 1, apologies, which is negative 2. So I don't think it's too terribly surprising, right? Because if I move forward, I'm moving down the parabola. So my derivative should be negative because my rate of change is that my z values are decreasing as my x values are increasing. In a similar way, if we hold x constant, say x equal to positive 1, then we get, I'm less good at drawing this one, so watch out here. Well, in fact, if x equals 1, then our parabola is going to be f of 1 comma y equal to 9 minus x squared minus 1 squared, or 8 minus x squared. Oh, sorry, 8 minus y squared, apologies. So it's going to look like, yeah, I'm really bad at drawing this one for some reason. I know why, so I didn't draw this. I need one more thing here. There we go. Sure, that'll make it a little bit easier. So we've got, yeah. So there's the parabola that we're traveling along. We're asking about the partial derivative with respect to y. So what we're saying is we're holding x constant, we're living in the plane x equal to 1, and then we're asking, okay, as y increases, as we move to the right, what happens to the z values? Well, at that point, the z values are also going to be decreasing, right? Our tangent line looks like this. And as we move from left to right, our partial derivative with respect to y is going to be fy is also equal to, or is similarly equal to negative 2y. If we plug in our point, fy evaluated at 1 comma 2 comma 4 is going to be negative 2 times the y coordinate, which is 2, which is negative 4. And although my picture might not do a very good job of depicting it, that red line is at a steeper slope than this blue tangent line. And that very kind of generically is what partial derivatives are all about. You're asking, how is the function output changing? How is the z value changing as either x is changing or as y is changing while holding the other things constant? I have, yeah. I'll also point out because it actually it's important here. I'll just say here, if you look at the second partials, my fxx is negative 2 everywhere. And my fyy is also negative 2. And there is a nice kind of connection between the second derivative's value and the overall function's concavity. So the second derivative in the x direction being negative means it's concave down in the x direction. In the x direction. Second derivative in the y direction being negative means it's concave down in the y direction as well. So we have concave down in both directions. Whereas like a saddle would be concave up in one direction and concave down in another direction. Also, yeah.
So you're saying like if we're struggling trying to figure out the graph of function we should try to.
No, I'm more saying that in a minute when we start talking about how to find extrema of functions of two variables, that this is going to be part of how we determine whether you have a relative maximum, a relative minimum, or a saddle point. That's what this is really looking towards, which is not too bad. It's, I mean, it's not the best, but like it's kind of of all the things we've learned, it's one of the more not terrible things. Let's see, what else have I got here in the last 5 minutes? Sure. So you don't have to limit yourself to functions of two variables when taking partial derivatives. For example, we could have something like f of x comma y comma z equal to x to the fourth times sine of y squared plus 3z. And then we could take all the first partial derivatives.
Is it possible? Like,
No.
I can't comprehend.
Right now, I'm not saying graphically this makes a lot of sense, but you can have functions of as many variables as you want and still ask questions about derivatives, even though there might not be a very good graphical interpretation of what's going on here.
Is there any?
I don't know, probably not. No, not real. I mean, not as far as I know. So, but if I want to find the partial of f with respect to x, well, easy enough. I have x to the fourth times a constant. How do I know it's a constant? There's no x's in it. So if your thing doesn't have the expression you're differentiating with respect to, it is a constant for all intents and purposes. So the derivative of x to the fourth times a constant is 4x cubed times the same constant. My partial with respect to y. Now I have a constant times sine of a function. So the derivative of a constant times sine, well, we did that before. The constant hung out, and we got our constant times the derivative of sine of some stuff is cosine of that stuff times the derivative of the stuff, which is 2y plus 0. Or just 2y. Similarly, our partial derivative with respect to z is also going to be x to the fourth times cosine of some stuff. But now when we take the derivative of the derivative of the stuff is 0 plus 3. And then it gets really messy when you start talking about finding second partials or mixed partials. Or you could have something like, fxxy, which notationally, unfortunately, would be the same thing as del cubed f del y del x squared. X first, x second, y third. X first, x second, y third. Do I really want to do it? No. But we could. It's not too terrible. Let's do it. I was worried it was going to have a product rule in there, but there's no product rule in there, so we can just do it.
There's no.
Product rule. I was worried
Oh.
I was going to have a function of x times another function of x, but I don't. So we already know that fx is this. So to find fxxy, I'm next going to find fxx. So again, to take the derivative of this with respect to x, I'm going to get 12x squared times still sine of y squared plus 3z. And now I'm going to take the derivative of that with respect to y. And now my 12x squared is my constant multiple that's hanging out. And the derivative of sine of some stuff is cosine of that stuff times the derivative of the inside, which is 2. That's not too terrible. But you can ask any amount of partial derivatives with respect to whatever variables you want for as much as you want. We usually are only talking about first and second partials, but you can go further. What else do I want to say here? Oh, yeah. No, we're out of time. Next time. Next time we'll talk about the chain rule. You might be like, James, you already talked about the chain rule. Well, there's a different chain rule for multivariable functions. It's kind of fun. Kind of get to draw a little picture and then like. All right. Have a great weekend. I will see you all on Monday. And you go back to the room I was in before because I do not have my cord. I should stop this before I get too crazy here. Yes.
First time coming to the co class,
Mhm.
but I was, you guys